Atomic structure chemistry, evidence for electronic structure. In other words, orbitals, how many electrons fit in each shell. The first half of this is HL chemistry, and then the second part is atomic absorption and emission spectra, which Miss Astrid, Miss A, kindly taught you guys because I was not able to be there, and I'm sure she did a much better job than I will because she's the best. Here's what we're going to be going over for the most part. We need to talk about the difference between first ionization energy, this is for sure an SL thing, and successive ionization energies, that is an HL thing. Understand how ideas about electronic configuration developed from atomic emission spectra, successive ionization energy. Once again, this is HL, this is SL. The fact that the first ionization energy provides blah, 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 blah. And then finally explain ionization energies and with regards to their nuclear charge, electron shielding, and other chapter 3 stuff. So I'm going to try my best to explain which parts of these are chapter 2 and could come up on the exam. That is for this chapter, and which parts are chapter 3 and will not ideally come up on the exam. But it's going to be very hard to adequately explain this without referencing chapter 3 stuff because the two ideas are so cohesively interlinked. It's hard to discern one from another. They are both intrinsic properties of the atom and therefore go hand in hand with each other. So I'm going to do my best, but I'm much more interested in teaching you correctly than teaching you for the chapter 2 test. So sorry, not really sorry. Happy to teach you though. Okay, so important definitions. We're looking for first ionization energy and successive ionization energy. The first ionization energy is the energy needed to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. There it is. Successive ionization energy is really the same idea as the first ionization energy. This is SL. Successive is really the idea of the first ionization energy, but repeated over and over and over again. So instead of it just being for 1 mole of electrons, it would be for the next one and then the next one. We'll get to that in a second. So anyways, write an equation for the first ionization of sodium. You have to have state symbols, and this is crucial because, as you'll notice, this bit being underlined, gaseous. This is to remove any, oh man, this is going to be chapter 4, but just trust me here. If you have 2 atoms next to each other, there's going to be some sort of attraction between them. It's the idea that water molecules stay close to each other because they are inherently attracted to each other. Whereas gas molecules around me right now, they're not necessarily all that attracted to each other. In fact, we assume that they're not when we do calculations. So in order to really isolate the energy needed to remove that 1 mole of electrons, we take something that might be in the liquid or the solid state, heat it up until it's a gas so that there is no longer that attraction, and then remove the electron so that we can really isolate the amount of energy needed to remove the electron and remove it from any other factors that might taint or sway that number, that might influence that value that it takes to remove that electron. So anyways, this would be the equation for the first ionization energy. You do not need to have this number memorized. You don't need to memorize this. We say thank you IB for the data booklets in this situation. You must for sure have the state symbols, and then notice we're only removing 1 electron, and we're only losing one charge, so there's only going to be one change in oxidation state. I'm sure some of you guys are thinking, oxidation state, what's that? It's been a long time. We haven't done that since last year. It just means charge. There's only one change in the oxidation state. It only went from 0 to +1. All right, so what affects ionization energies? This is really going to be chapter 3 stuff right here, these ideas, but it is important to talk about them very briefly. I would say you might not necessarily need to write this down, but you're going to need to know it eventually, so why not, right? Electrons are held in their shells by attraction to the positive nucleus. In other words, opposites attract, opposites attract. It does not look like how you spell the word opposite, but I'm not good at English. This attraction must be overcome to remove an electron. In other words, I need to put in enough energy to pull the electron away from the nucleus. Think about pulling the moon away from the Earth. The gravity is holding us together in orbit, so you'd have to put energy in to remove it out of that orbit. The outer electrons are furthest away, so they are the least attracted. Same idea, if you want to think about it like magnets even. The farther magnets away, the farther magnets away. Let's try this again, Mr. Parks. The farther two magnets are away from each other, the easier it is to separate them because they're not as attracted. Therefore, they are the easiest to remove and remove first. In other words, I'm going to put this in layman's terms. Valence electrons are removed first because they're on the outermost shell. They're farthest away, so the attraction is the weakest. They're the easiest to pry away. Whew. All right. The nuclear attraction is affected by 3 things. Here we go. Atomic radius. I'm gonna do this in terms of a physics equation. And some of you hate this, and some of you might not enjoy this at all. Some of you might love this, but it's a great way to think about it. Nucleus, electron. So the strength between the strength of attraction between two charged particles is exhibited by this equation. The force electric is equal to kQq over r squared. And Q is the charge of the nucleus, and the other Q is the charge of the electron. So, and then r is the radius between the two charged particles. So, in other words, if the radius is bigger, you're going to be dividing by a larger number because r squared is on the bottom, and the larger the denominator gets, the smaller the whole number gets as a whole. So the larger the radius, the less the attraction. The smaller the force electric gets. Nuclear charge, in other words, how many protons do you have? The more protons, the stronger the attraction. That is going to be affecting this Q right here. So the more it goes, the more Q goes up, the more the force electric goes up. Let's go back to the radius. The more the radius goes up, force electric is going to go down by a squared function. And then electron shielding. This is the idea that if my nucleus is here and I've got a bunch of electrons sitting around it, and this is my electron of note, all these shielding electrons, the inside electrons, are going to repel my most outside one away. In other words, what that really means is it's just going to have an impact on radius. It's going to push the farthest one even farther out, increasing the atomic radius, making the attraction even lower. So electron shielding is really just a way of describing atomic radius indirectly. Once again, this is all chapter 3 stuff. But it is going to be necessary for you to know this, and the more you hear it, the easier it's going to get. Definition: electron shielding. Electron shielding is the repulsion between electrons in different inner shells. In other words, if you've got 4 shells and 3 of them are on the inside, those 3 are going to push out the 4th one even farther. Shielding reduces the net attractive force from the positive nucleus on the outer shell. So I'll draw it out again. If this is my nucleus, and I've got a bunch of layers of electrons that sit like this, and then this is my last one, all of these electrons are going to push out on this little cyan is the actual color, valence electron. So the more inner the more inner shells you have, the farther the valence electron is going to be, making it easier to remove because it's farther from the nucleus. Therefore, the nucleus can pull on it with less force. All right, so let's just practice really quick. Write an equation to represent the first ionization energy of oxygen. Oxygen goes to, remember, first ionization energy is when we are removing first electron. So then oxygen will turn into oxygen plus. And since we removed an electron, that means we better show that it got ripped away, and we should show that it's going to come out as a product. Please remember that your reactants and your products these things should be equal in charge. So on my reactant side, I have a neutral charge. And then on my product side, I have a +1 and a -1. In other words, this is also neutral in charge. So that's good. That's a good way to check it. Oh, looks good, right? No. No. Definitely not good. Because we're forgetting our state symbols. You have to say it's a gas. If you don't say it's a gas, I have to mark you wrong, and then we both aren't happy, and we're both sad, and I don't like being sad, and you don't like being sad, so just write it's a gas, and we can both be happy. You should see it underneath my writing. Successive ionization energy. This is HL. So then, if you wanted to skip this, SL students, go for it. These are the energies that are needed to remove each electron in turn. So, second electron removed, how much energy? Third electron removed, how much energy? And these would be specific quantum of energy. It's going to be a specific number. So the way this would look would be as below. So the first 3 ionizations energies of lithium look like this. This would be the first one. This is second. And this is third. You're going to notice that these are all going one at a time. So if the first one ends with a lithium plus, the second one is going to start with a lithium plus and end with a lithium 2 plus. And then the third one will start with that lithium 2 plus and end with a lithium 3 plus. Other things you should notice. Drastic changes in the amount of energy needed to remove each electron. This is actually very important. These values are specific to lithium. Each element and each ion will have its own specific ionization energy. Lithium is a little bit different. Very rarely are you going to see changes in energy from the first ionization energy to the second ionization energy, and the second to the third this large. These changes are massive, and you'll start to understand why. And if you don't, this is going to be a problem I'm actually going to ask you, because there are very clear reasons why it goes from 520 to basically 7,300 to about 12,000 kilojoules per mole. And we'll talk about this. I'm not going to tell you the answer right now, though. Okay, so then what do you notice about each thing? I just talked about this. Can you explain this trend? I do want you to kind of think about why you see these massive changes in ionization energy. I'm not going to give you the answer in this PowerPoint, because I do want you to think about it when you're done watching this and getting the notes. I want you to kind of hypothesize why this is. And ideally, you should be able to answer this, but it is going to be a little tricky. I'm hoping you can answer this, and if not, I'll be happy to walk you through this. By the end, everybody will get it. Key things to remember about successive ionization energy. Each one is going to be greater than the first one, and this is because you have less, for each electron removed, there is going to be less repulsion. Therefore, the remaining electrons are drawn closer to the nucleus. You should be thinking that if there's less electrons there, they're going to be pushing against each other less, so the atomic radius is going to get smaller. And if it gets smaller, then those electrons are closer to the nucleus. So the nucleus is going to be able to hold on to them even tighter. Going back to the idea of Fe is equal to KQQ over R squared. Every time you remove an electron, this is going down. Therefore, your force electric is going to go up. And it's going to go up significantly because as the radius changes, it's a squared function. Looking at successive ionization energy tells us two things, and this is really going to be hinting at electron shells here. Successive energy, this is a tongue twister. Some successive ionization energies are close together. Occasionally there's a large jump. This is evidence for discrete shells. In other words, this 2-8-8 pattern that you guys have been talking about or seen before. We can also see the number of electrons in each shell. Once again, this 2-8-8, the idea that there's first energy level, second energy level, third energy level, and the first one holds 2 electrons, and the second one holds 8, and the third one holds 8. This is how we were able to start to deduce this information, when we were able to really start to pump in enough energy to successively remove electrons from atoms. So this is nitrogen. It's going to be easiest to understand this if we start off by looking at the electron configuration and orbital diagram of nitrogen. So I'm going to just write it out. So nitrogen is 1s2, 2s2, 2p3. So if we were going to do this in terms of an orbital diagram, 1s, 2s, 2p, 1, 2, 3. The orbital diagram is going to become very useful to you when explaining more subtle jumps. For right now, it shouldn't make a whole lot of sense to you what I'm saying, but we'll get to an example with chlorine. What's important to see here is that on the second energy level for nitrogen, there are 5 valence electrons. So there are 5 total electrons in the second energy level. And when we start to do the ionization energies of nitrogen, we saw this pattern here, where the first 5 were less difficult to remove than the 6th one. So the first one was the easiest, and the next one was a little bit harder, and then a little bit harder, and then this pattern I'm going to get into a little bit more. this jump gets to be bigger than the rest of them, comparatively speaking. And so the first time we removed an electron, we removed a 2p. And the second time we removed another 2p, and the third time we removed another 2p, and then the fourth time, which was from here to here, we had to break into the s orbital, and then we had to remove another s electron, and then all of a sudden we lost the entire second energy level, meaning we had removed enough electrons so that the second energy level was no longer occupied, and we were able to only have a situation where it was nitrogen with 2 electrons, and those 2 electrons were on the first energy level, which to begin with is already very, very close to the nucleus, so the attraction is incredibly strong. And then on top of that, we had removed 5 electrons, so then there's a ratio of protons to electrons of 7 protons to 2 electrons, which is incredibly disproportionate. The number of protons is so much more greater than the number of electrons that the attraction is insane. But that still doesn't explain why this massive jump occurred, because just previously on this green one here, we had a ratio of 7 protons to 3 electrons. So then if energy levels didn't exist, hypothetically speaking, our next point on the map would have been somewhere about here, just slightly higher, nothing super significant, but we saw instead this massive jump, like a 5-fold increase. And that was when it started to dawn on us as scientists and chemists, something's not right here. This is telling us something. And from that, we were able to figure out that there must be these electrons organized in these orbitals, these rings around the nucleus, like moons orbiting a planet, where the closest ones to the nucleus are much more attracted. So this massive increase was telling us, in part, electrons exist in shells, and those shells exist in layers around the nucleus, which is at the epicenter of the atom. We can continue to see this pattern. So in this situation, I believe we're looking at, magnesium. And magnesium has 2 valence electrons. So once again, I'm going to write this out in terms of an electron configuration for magnesium, and it's going to be down here. So 1s2, 2s2, 2p6, 3s2. So then the first 2 electrons we removed, we saw, a relative, it was an increase. It wasn't anything crazy, but it was an increase. And those 2 electrons were us dropping out the 3s2 electrons. So we removed the first 2 electrons and removed the third energy level. So then if we had a nucleus, and then first energy level of electrons, second energy level, third energy level. When we removed those first 2 electrons, we effectively got rid of this third energy level. And then we had to start to access electrons that were in the second energy level, which was much closer to the nucleus. So once again, referencing this equation, since we are accessing electrons that are now in the second energy level, the radius is much smaller. So the radius between the nucleus and these electrons went down, therefore the force electric went way up, and we can see that difference in energy from the second ionization energy to the third. And then we just kept removing electrons because as scientists, that's what we do. We just keep doing things until we notice a pattern, and then we start to take that data and make sense out of it. And then we got 1, 2, 3, 4, 5, 6, 7, 8 electrons, and then we removed another one, and we saw yet another massive jump. So then what we were able to figure out from this was there must be 8 electrons in some sort of a pattern that makes sense, and they must be relatively the same distance from the nucleus, because the second we removed that 9th one, we had another huge jump in energy, which would indicate the radius once again got much smaller. So this bit of information started to let us know that not only are electrons organized in shells, but now we're starting to figure out how many electrons exist in each shell. We're starting to see that there are 2 electrons in the first energy level, and then after that there are 8, and then after that, and so on and so forth. We start to really deduce and start to analyze and figure out the number of electrons in each energy level and the relative location compared to the nucleus. Oh, the beauties of this. Let's just take a second and start to really draw out the finer points of this data. So we're going to start out by doing the electron configuration of chlorine here. 1s2, 2s2, 2p6, 3s2, 3p5. Great. Electron configuration is nice to get a basic idea of what's happening, but in this situation, it's not going to tell us the whole picture. We need to instead do an orbital diagram. And this is going to be a little tight for space. So the 1s is going to look like this. 2s is going to look like this. 2p. 3s looks like this. And then 3p. 4, 5. Great. So, remember, so this is a bit of a review. When we're doing orbital diagrams, we have to really obey 2 major laws. Aufbau, which says that we put electrons in the lowest energy levels first, the first energy level, and then we successively build up from there. And then Hund's rule, which dictates that every orbital will get 1 electron before any orbital gets 2 electrons. And that's because if you put 2 electrons in a single orbital, they're going to start to repel each other, and then naturally that second electron will fill the empty space of the unfilled orbital to reduce repulsion. So then if we're going to remove electrons from an atom in successive ionization energies, what we're really doing is we are undoing Hund's rule. So we are going to reverse Hund's rule. So remember, Hund's rule said that electrons fill unfilled orbitals before they start to double up in a single orbital. So if we're going to undo that, naturally the farthest electron away, the easiest electron to remove would be, this guy right here. Or I guess if you wanted to say, you could say this other electron. Really, one of the 2 paired electrons in the p orbitals. Since there are 2 electrons in that orbital, they're going to naturally repel, meaning they're naturally going to be farther away from the nucleus, so they're going to take less energy to remove. So then what we started to see was this. In chlorine, the first 2 electrons we were able to remove have these ionization energies. At this point, you're going to start to be thinking, oh, well, Mr. Parks, the second ionization energy is much bigger than the first ionization energy. It's about 1,000 more kilojoules. And yeah, you're right. But remember that successive ionization energies, no matter what, will be higher than the previous one. So the fourth ionization energy will be higher than the third, and then the third will be higher than the second, and it's just because you have less repulsion. So no matter what, the more electrons you remove, the higher the ionization energy will be, because those electrons will get closer to the nucleus, and that nucleus will be able to hold on to those electrons tighter. So to think that is correct, but it's not as deep as you need to be looking at here. So what we're seeing here instead is this. This column is going to be important. This third column. The third column, the third electron that we remove, is when we are going to start to, and I'm going to just color in, I'm going to scribble out these electrons that we did remove, and I'm going to use black to do it. So this current state would be Cl2+. What you should see here is that in my 3p orbital, it's going to look like this. 3p, I'm going to have 3 electrons, and they are going to be occupying unfilled orbitals. In other words, the amount of repulsion between them is going to be the lowest it could be at that moment. They're as spread out as they could be. And if the repulsion is low, so relatively speaking, the repulsion is going to be low, therefore the attraction between the nucleus and electrons will be a bit higher. And then what we can see here is there's a much larger jump in terms of the change in ionization energy. I needed to put in an extra 1,500 electrons just to 1,500 kilojoules per mole just to remove this one electron. And that's because what we say then is if you ever have a situation where you have a half-filled set of orbitals, we call this a semi-stable state. It's the idea that these electrons can be pulled as tightly as they could to the nucleus while still being there. There's not as much internal repulsion between the two electrons in the orbital. So then you'll start to continue down, and then you can see, you can even kind of see that to remove the 3p electrons, on average, the change in ionization energy is going to be larger than the change in ionization energy between removing these two paired p orbitals. So this corresponds to this here, and then my reds are going to correspond to these three. And then we get to the fifth ionization energy, which is going to essentially be, and I'm going to do this in purple color, we are going to have a Cl5+. The fifth ionization energy means we have 3s with 2 electrons filled in there. Then we got 3p1, 2, 3. And we've removed the electrons that are in the p orbital. And then you're going to see yet another significant jump in the difference in ionization energy needed. This is showing evidence for sublevels. The idea that the s orbital is going to be closer to the nucleus than the p orbital would be, and that they're going to inherently be tighter in there, and since they're closer to there, the energy difference needed to remove an electron from a subshell closer to the nucleus will be larger. I'm expecting to have to explain this a few times to you before you get it, and that's not because I don't think you're intelligent, but because this was explained to me maybe 70 times before I finally got it. And I'm assuming you're smarter than I was at your age, so I'm expecting it'll only take me like 3 or 4 times. This is just my way of saying this is a very tricky concept. To take this data and interpret it into a meaningful idea and visualization of the atom. So if you don't get it right now, that's fine. This is just your first time hearing it, and I would love to draw you a picture in 20 different ways until you really understand it. So don't feel like you need to get it right now. The last little bit that we should be noting is after removing our 3s and we remove one more, we can start to see the real jump when we go from third energy level to removing an electron in the second energy level. The radius is going to be much lower, much lower. Therefore, the ionization energy needed is going to be much higher. You got to really put in some effort to rip that away. This is here to really hammer this idea home. I'm going to just put down the electron configuration of the outermost sets of these things. So for example, lithium, it just has a 2s1. All right. Beryllium is going to be a 2s2. So if we were removing the electron from beryllium, we're going to be entering into the 2s orbital. So it's going to take more energy. Next up, we're going to see a decrease, and that's because what we have here is 2p1. We have an orbital. We're going to be removing an electron. Removing an electron farther from the nucleus than the 2s, therefore less energy needed. And that's what describes this downfall. The next time you should see a downfall that looks like that is going to be here. And that's because oxygen is going to be a 2. A 2p4. In other words, it's going to look like this. 1, 2, 3, 4. We have on our px orbital repulsion of electrons in same orbital. Oops, that's an ugly B. In same orbital, therefore lower energy needed. Across the period, meaning across the row, this same pattern, it follows true, where it goes up, down, up, down, up, way down. And this way down is just going from, this is 3s1, meaning we're going to be removing an electron from third energy level. So it's going to be much farther away. So then it's going to take much less energy. In fact, it's going to take less energy than if we were removing it from the 2s orbital. So if you could imagine francium on the bottom of the first column, which is going to be, 7s1, the amount of energy needed to remove that electron from francium would be next to nothing. And that's just because the radius of that atom is so large that the nucleus it's barely strong enough to hold that outer electron in orbit. So the energy needed to remove it is very little. All right, so if we need to use ionization energies to work out what group an element is in. Side note. This is when we start to get into SL stuff. SL also needs to be able to do this, but it's for chapter 3, so watch it if you feel like you're incredibly well prepared for the chapter 2 test and you just kind of want to start to move forward. I'm going to trust your judgment on this. So anyways, SL chapter 3. So magnesium is in group 2. That's a fancy way of saying column or family 2 on the periodic table, and it has successive ionization energies as such. Remember that if something's in group 2, that means it's got 2 valence electrons, which should be relatively easy to lose, like we see here. And then we see this big jump in ionization energy, which indicates that we are now, on this one, removing from an inner level. So the radius went down. Using this pattern, you can start to, you can deduce what group an element is in. So for example, if we had to figure out what atom this set of data belonged to, we're seeing this big jump between the 5th and the 6th. So what that means is if we removed 5 electrons, therefore this atom must have 5 valence electrons, therefore group 5. Cool? I will explain this to my SL kids in much more detail because I don't like the way I'm doing it right now. All right, so on the axis below, this is just another practice problem. Estimate the successive ionization energies of oxygen, and the second ionization energy has been added for you. So then oxygen, periodic table, I know there's 6 valence electrons. I'm going to get fancy with this. So then what I'm going to do then is 1s2, 2s2, 2p4. So the first energy, ionization energy, is going to be lower because remember I've got 2p. And the first ionization energy is going to be removing a paired electron from an orbital. So then I should have a relatively larger, sorry, not like a removing from a lower energy level larger, but just a tiny bit bigger jump from number 1 to 2. Numbers 3 and 4 should be relatively the same, just a slight increase because your ionization energy should always increase, which would then indicate all 4 of my p electrons. I'm going to switch colors to make life easier. Now I'm going to start to remove the 2s. So I'm going to make sure it's going to be just a little bit larger. And then 6 is going to be there, which would take care of both of my 2s. And then now I'm getting into the first energy level. And because I can, I'm going to put it way up here. Because I know that the spike in ionization energy is going to be huge. And then the last ionization energy is going to be larger because they're always larger, just not a whole lot larger. So then this is what I would expect the graph to look like. We're just trying to sketch it. It doesn't need to be immaculate. It doesn't need to be perfect. And also it's telling us we don't need to join our points. So I'm okay with this. This is what they go with. And they're telling us this kind of stuff. Even they know, the creators of the mark scheme, they're telling us we don't need to pay attention to the 2p and 2s true jump, the idea that it's being removed from a closer energy level. But we're fancy. We're going to do it because that's what we do. We're perfect. And yeah, the rest of it looks pretty good. But I'm seeing this large jump here. And this also went up. So yeah, I would say we got our 2 marks here. Happy face. Oh, that's a terrible happy face. There you go. It's better. Cool. everybody needs to know this. Atomic emission spectra also provide evidence for the existence of quantum shells. In other words, the idea that there are energy levels that are successively farther out from the nucleus. Miss A did this with you guys, so this is just a review, I hope. So remember, absorption spectra is taking energy, and emission is going to be releasing. So in the picture here, this would be absorption, because that photon is going into this electron, and then that electron is going to take that energy to jump up to a higher energy orbit. There are specific lines that are discrete in their quantum. In other words, it takes very specific amount of energy to make these jumps. It's not like if I sent a wavelength of 500 nanometers and I sent somewhere between like 495 and 505, it's not as if a couple of those wavelengths are work, or like, oh, those wavelengths are close enough, it's good, that'll work. No, it's very specific amounts of energy, and that's indicated by these definite lines that are appearing here, or the absence of those lines down here. Specific amounts of energy, so energy specific, which then indicates the energy levels. Oh man, I'm struggling to spell. Energy levels are also specific, meaning the third energy level sits at a certain radius from the nuclei, and you need to give it exactly that. You need to give the electron exactly that much energy to get to the third energy level. If it's in between there, if it's a little bit below or a little bit above, it won't work. You need to hit exactly that amount of energy to make that jump. And it is specific for each element. So in other words, every element has its own fingerprint. Fingerprint is just an expression. Every element has its own traces of emissions and absorptions, and we can use that to identify which elements are there, or since we've gotten to the point in life where we know all this information, instead what we do is we take these gases to produce neon lights that have a really nice, a very beautiful red color. Or we'll use sodiums to make a nice yellow color, or what is it, cesiums or potassiums give us a beautiful purple color light. It's just what we do. So a lot of the lights that you're seeing are just tubes of gas that we provide perfect amounts of energy to, so that we get the colors of light that we want. So then what we can start to determine from this is the specific transitions needed. I know Miss A did this with you, so remember that E is equal to HF and C is equal to lambda F. I believe you guys know this is E is equal to H nu, and C is equal to lambda nu. It's the idea that this wavelength of light can then be used to determine the frequency of that light, which can then be used to determine the energy between 2 to 3. How much energy is there needed to move an electron from energy level 2 to 3, and then that corresponds to the visible spectrum. We can actually see this color. This is the Passion series. So that's how we're able to translate the idea of the emission spectra into which transitions are happening. if you're looking down on this end of the spectrum, you should notice these lines are converging. They're getting closer together, and they are at lower. One sec. They are at lower wavelengths, which therefore means higher frequencies, which therefore means higher energies. And all I'm doing is following this through to its algebraic conclusion. Just a substitution problem where I end up with the answers of E is equal to H C over lambda. It's just a set of algebraic expressions where we can deduce this. If you're not super solid at algebra, talk to me. I'll explain it to you in more clear terms. But from this, we know that since the lines are converging at higher energy levels, we can determine that higher energy levels are closer in radius and really just energy until we get to the point where n equals infinity, in which case then we say this is ionization energy. So if we can ever give an electron enough energy to take it to an energy level that is infinitely far from the nucleus, then the nucleus can no longer hold an attraction on that electron, and it is then a positively charged particle. Oh man, this is a lot of writing. I don't know why I did this. Okay. This is really just a summary that I have. It's a summary of what I have said. I'm going to just let you pause this and read it on your own. And if you have questions, let me know, because me reading it out loud doesn't do anything for you. Okay, moving on. Okay, so we should start to see here a couple of things. Here we have our converging energy levels. As n gets to infinity, this was exhibited by, in the last slide, those lines in the emission spectrum near purple that are getting closer and closer together. Purple has a higher frequency. So then that's as they get to infinity. So as this electron approaches infinity, so the idea that this electron is so far from the nucleus can't attract it anymore, we get the ionization energy. And that is explained up here in this top box, and I feel like it's explained relatively well. Things that are important to know in this situation. Since energy levels farther from the nucleus are closer together, then it's safe to assume, and that I guess it's also noted or known, that energy levels closer to the nucleus would be farther apart in terms of energy. So this will be from n equals 2 to n equals 1, the largest difference in energy. Therefore, this would have the highest frequency to the point where this is also going, where this is going to emit ultraviolet UV rays, or electromagnetic radiation. This is going to emit ultraviolet electromagnetic radiation. In other words, if there's ever a transition from n equals whatever to n equals 1, we won't be able to see it because it exists at a frequency above the visible spectrum. Our eyes cannot register it. The only one that we can actually register is from anything from n equals blah to n equals 2. This will give us visible light. Everything to n equals 1 will give us UV light. And then on the other end of the spectrum, I'm running out of colors, green. We get infrared. This all goes back to the electromagnetic radiation spectrum, EMR. And there's a really nice diagram in your book, and it's all inversely proportional to the frequency, but I feel like this video has been going on long, so I don't want to labor on that. I will talk to you about that in person if you don't get it, so please just talk to me then. All right, practice questions. This is, I believe, the last one. Write an equation to represent the fourth ionization energy of chlorine. I'm not going to do this for you. I want you to give it a shot on your own. HL. Sorry, this is HL. Sketch the graph you would expect for the successive ionization energies of aluminum. Once again, this is HL. An element in period 3 has the following successive ionization energies. Blah. You can read that. What group is it in is what I'm looking for then. Identify this element. This is SL chapter 3. Give it a shot at the very least if you want to, because I mean it is chapter 3 and we are supposed to be doing chapter 2. So if you want the extra practice, go for it. Oh man. If any of these objectives weren't clear to you, and I'm not a big objectives fan, but I do think it's a good summary for this video because it was a lot. If any of these weren't clear to you, let me know, and I'll do my best to explain them in person. But let's stop here because this video went on forever. Have a good day, guys.